Ladies and gentlemen, we'll continue our exploration of dynamical systems with application to climate. And just to, again, the slides are available for today, so you can download them from that link. So maybe to follow up on yesterday, I showed you this null hypothesis for sea surface temperature variability. Now be careful, this is sea surface temperature variability null hypothesis. It's applied everywhere. You see everywhere red noise spectra as a sort of statistical test, but for many of the other quantities you don't know whether that's a good null hypothesis. For instance, for sea surface height, you can actually show that it's CAM noise, it's not red noise. It's sort of correlated additive and multiplicative noise, and it has a different PDF. It looks a lot like red noise, but it has a different PDF. And so for other quantities, for instance land ice or some other, say, quantities, you don't know unless you do sort of detailed modeling on what would be a null hypothesis for, which is how the variability would be driven by, say, white noise. So, but for sea surface temperature we derived this, and there was a good question afterwards from two of the students to how you do this now in practice. And I didn't mention that. We mentioned the AO1 process, but it was a bit quick. So what you do is you have this continuous Ornstein-Uhlenbeck process, and you can say, well, if I label xtn plus 1, if I label that as xn plus 1, and I apply that formula at t is n plus 1 and tn, then I get xn plus 1, or maybe write it out first. Tn plus 1 is equal to, you get e to the power minus gamma tn plus 1. I get here an x0, and I get here sigma integral tn plus 1, and then I get e to the power gamma s dws. Right, so that's just at tn plus 1. And then I also can do that at xtn. So I get gamma here, I get tn, and I get here sigma integral tn, same integral, ds. And now I multiply this by e to the power. Of course I want to subtract them, so I get minus gamma. Then I get here tn plus 1 minus tn, and I do it everywhere. And then you see that when I look at this, I get sort of x tn plus 1 minus e to the power minus, and now I put here gamma delta t, where delta t here is obviously tn plus 1 minus tn. And now here I get x, say, tn is equal to, and now you see that these ones here, they cancel, because you get a plus gamma tn, which cancels this one, and I get the same factor here, so this cancels. And you get in the right hand side, you get something like e to the power minus gamma tn plus 1. This is the same term as this one when I multiply, and then I get the difference in the integral tn plus 1 e to the power gamma s dws. So this is then sort of the discrete process. So you label this now as x n plus 1, and now you write it in the right hand side. You get alpha xn plus some stochastic term, and this is then sort of the coefficient alpha here, which is between 0 and 1, right? Because delta t is finite, so this is between 0 and 1. And this is the red noise discrete process, right? And so what you do in practice, you estimate this. So this is the AO1 process. And what you do in practice is that you estimate from the time series, you estimate the alpha, and then you do an enormous amount of realizations for different, say, noise forcing, and then you compute the spectra of this AO1 process, and then basically you look at the 95%, say, maximum in the spectra, and that will be your sort of 95%, confidence interval for showing that how the time series extends above the red noise. Yeah, so how you do that in practice? Well, you don't have to do that because it's done already in the Climate Explorer very well. So it looks that So if I do that for the Nino 3.4, here. So this is the Nino 3.4, say, time series. And now you want to show that whether this is sort of extends red noise, right? Whether there's variability in here which cannot be explained by pure mixed layer noise forced variability. And then you look at spectrum. So you say spectrum. Now you have to know a bit about this, but you do a spectrum. I'll smooth a bit in the bins. So let's take 5 bins smoothing. Then I take all months together because I want to have an anomaly over the. I select over 12 months. So this is the anomaly with respect to the seasonal cycle. This is already subtracted. I normalize it here, and I don't have to. I detrend it. It's also done already, and I do it. Now it says here warning, right? The spectrum routine often produces nonsense results. This is true. Well, everybody knows that. You have to be very careful with computing all this data analysis. But this is, you have to fine-tune this a bit in terms of the smoothing of the bins, and you can do a lot more in detail. But that's not, not my main point. Now, what it's done here is that this blue curve here, it's shown a little differently here logarithmically, and it's also with the period instead of the frequency. But you see that there is variability in this period between 2 and 7 years or so here in the Nino 3 series, which extends above the red noise. And the Climate Explorer also explains it. It says here the 95% highest spectrum of 261 AO1 processes. Not going to explain why it chooses 261 here. But and then it says here the peaks here, which have a certain significance. So this is a, yeah? Sorry? Yeah, the blue curve is the red noise spectrum. So this is this 95% red noise spectrum. So what it's done is you take in this case 261 realizations where the autocorrelation was fitted from the Nino 3.4 time series. And then you look at all those spectra and you look at the 95% highest spectra here. Right? So 5% of the spectra exceeding this one here for every frequency. And then you plot this and then basically you see whether it extends it. Now, it's fun if you like this. Try to do it with other time series. There's a lot on there. NAO, AMO, all those things are on there. And try to see whether you can get it above red noise. It's funny to do it. Yeah, I don't have time to do it because it's not topic of the class. But this is the answer to. I don't know who asked that. You asked that. No. Yeah, I think so. Okay. Well, I don't remember. But anyway, this is the answer to hopefully the question. Yeah. Yeah, this is in practice you take white noise here. Yeah, you can show that this is following and the distribution of this thing here is n mean 0 and sigma squared variance. Yeah, I don't show that. I mean, you can. It's probably in the notes, but I'm not sure. Otherwise, you have to put it into the notes. So I hope that answers that question. And now we go to the next problem. Now we know for sea surface temperature at least the null hypothesis. Now the question is, how do preferred frequencies of variability get into the climate system? Right? This is the next question. If it's not externally forced directly, that must be internal, and it must go through instabilities, that you all know. Right? You know baroclinic and barotropic instability, which are all, internal processes which give you sort of preferred frequencies into the flow, for instance, in the atmosphere or in the ocean. So to illustrate this, and this is probably the easiest example, I start with a very long time scale phenomenon, which is the Pleistocene ice ages. So again, this is this questionable figure, but at least it sets the scene that I can point out which time period we focus on. So it's here between, say, 20,000 year and 400,000 year variability. So we're really in the geological area, proxy data to use. And we're going to focus on how those frequencies get into the system. And now you think, that's easy, because I know already that some of those things are externally forced. I'm going to show that in a minute. But watch what happens. So this is a nice overview of what happened the last 5 million years. Starts here at 5 million years. And you go to present day here, and this is the oxygen isotope ratio from sediment cores. So it's calcite, say, animals, and you can look at the oxygen isotope of those animals in the sediments, and you can reconstruct there a temperature signal by calibrating that to, say, present day type of how animals have this distribution. And then what you see is that, so this is a measure of temperature. Now this can also be connected to delta temperature records in ice cores, which are over the last 800,000 years, so that's this period here. And then you see that, well, the Earth cooled, right, in general. This is a cooling. And what you see is also that, well, there's some say, bathymetry features. There's closure of the connection between North and South America, which caused actually quite some effect in the ocean circulation. And then what happened here is that you have this, say, what we call a 41 kiloyear world, so where the variability here is dominantly sort of dominated by 41,000 year variability in this ocean sediment core isotope signal. And then at some point here, and here we call this the mid-Pleistocene transition, suddenly the variability is dominated by 100,000 years. And you all know this. This is the classical ice age problem. And the question is, well, where does this time scale come from? Well, this was, of course, initiated by Milankovitch, which you all heard of, I suppose, that if you look at the external forcing, then there are dominant frequencies in insulation, and they're listed here for precession, obliquity, and eccentricity. Now you see that for eccentricity there is some kind of 100,000 years type of signal, but if you look at the signal of the eccentricity, it's extremely weak. So if you compute an insulation changes due to eccentricity alone, it's very difficult to explain why you get 100,000 year, say, frequency in there. Now for the 41 and for the, say, 20,000 year variability, you can look at the forcing. Now this is a typical forcing at 65 north at the summer. And then you see fluctuations here, of 100, maximum of 100, say, watt per square meter. And this is seasonal varying, right? Annual mean, it is 0, because this obliquity and precession don't give an annual mean signal. Only the eccentricity does this. And so you can imagine if you put that on the climate system, you would expect to see, 41, and you would expect to see 20,000 years, but you would not maybe expect to see the 100,000 years. Whereas this is dominating in the spectrum. So this is the main problem. When you look at the forcing, and this is the spectrum then 1 over kiloyear, you see dominant frequencies here at these, say, orbital frequencies. And then when you look at, say, the spectrum of the oxygen isotope series, you see very clear power somewhere else. So the forcing doesn't match the external frequency. And this is, of course, it's a famous, say, I would say, unsolved problem in earth sciences. And it's awaiting, there are many theories on this, and it's awaiting a acceptable solution. Now, where do you think the problem is in terms of, it's good to think about that. Why would it be difficult, there's maybe 6, 7 theories or so how this comes about 100,000 years. So where would the problem be in falsifying any of the theories? Exactly. It's nonlinear. Where do you think the nonlinearity comes from? Yeah, but now I want to have physics in processes. Where is the nonlinearity? Nonlinearity comes from somewhere. In atmospheric flows you would have advection, right? Very strong nonlinearity. And on this long time scales, where would you think that the dominant nonlinearities would come from? That would be very nice, but that's even on much longer time scales. That's where really the solar system gets, chaotic, and that's, few 500 million to a billion years or so. Freddie knows better because he's working on it, but then that's much a longer time scale. Ice sheet, very good. Ice sheet is one of the things which is very important. The other one is carbon, the carbon cycle, right, which plays a role. Now, the problem is why you difficult to falsify it, because you have only single time series. You know, if you would have a spatial pattern of all those Pleistocene ice age where where it would distribute it, then you could also look at the spatial pattern for verification, right, or for falsification. Here you have only a few, at a few locations you have time series, which makes it very difficult to falsify any of the theories. And so there are many models, and you see that actually this Pleistocene ice age problem has been stuck, if you look at the model hierarchy, into the more conceptual models, with maybe a little bit into more the intermediate complexity models, but not in the full GCM ranges, right? Also because of computational limitations, right? You have to integrate a full-blown GCM if you want to do that for a few 100,000 years, which you know is very expensive. But also that's why it's hanging in this conceptual model framework. Now there's a tight coupling, as I said, between CO2 and temperature, which you see here. So there actually is, so the CO2 is the dashed curve here, and the temperature here is the drawn curve. And you see very close, say, relationship. It's also interesting why the CO2 remained between 180 and 280 during this, say, period. So time goes from right to left. Always in the earth sciences they do it the other way around. They plot time from right to left. And this means also that the carbon cycle and temperature is tightly coupled. And so you cannot do without, you cannot do only physics. You have to do also, marine biology and carbon cycle modeling to really solve this problem. And that makes it also very difficult. Now, people have, of course, come up with many ideas. I've no time to give an overview of that. It's not in this class even, it's not important. What I want to show is a very old model, and because you're going to work with it. This is, it's a model where you easily work with. And it's a model involving 3 components. So it's the ice mass, right? So imagine that it's integrated over the globe. And then you have the carbon dioxide concentration in the atmosphere, that's mu. And then we have a sort of average ocean deep temperature. So the ocean is also involved in this model, which you can imagine because the ocean circulation transports heat in the system, which also affects, of course, the ice sheets and the carbon dioxide. Now, to get a little bit feeling on what is contained here in the equations, when CO2 goes down here, mu, you would expect that the ice sheets grow, right? It gets colder and they grow. So all those mechanisms are sort of included here. The alpha 1 and all the other parameters are constants. Well, you're not interested in all those constants, how they're determined. That's all in Salzman-Maas paper. Not going to discuss that. There are feedbacks in there. You see here this feedback here with mu, which is the solubility pump in the ocean, where you have in that CO2 increases, temperature increases, and you get outgassing of CO2. And this is also you see also damping effects on there. You see also that there's a local damping of the temperature with these constants, and there's one forcing here. And that's sort of the forcing of CO2. So that's emissions of CO2 just to natural causes, or decrease of CO2 due to weathering, which is also in this F mu. So we're not going to consider all the other parameters, right? We have fixed them, and we only consider F mu. And now we're looking at it as, well, this is an example of a nice dynamical system. Let's see, I can wipe this out. F mu is just a forcing of CO2. It can be biogenic or can be due to weathering. So it's a source and sink of CO2 in the system. No, you can bring it in. This is an extension of the model. It's also in the MATLAB codes which are available. You can put the insulation in. But this model already shows you, that's why I use it, variability without the insulation variation. So it's internal generated frequency. And so you can write this as, of course, as x dot is, say, fx, and lambda here I put f mu. This is the parameter. And we call this now, so x is, say, the vector I, mu, and theta. So it's a 3-dimensional vector. And we call this here an autonomous dynamical system because this thing doesn't depend on time. If you put time here, there could be, so if you have insulation there and you have time there, then it's a non-autonomous system. But the easiest dynamical systems are autonomous systems, and that's why we start with those. Okay, and now what you can do now is what you would do probably too. At least what would you do? Maybe I ask the question. Well, you do that, but what would you do? I mean, normally you have a model, right? And you take, say, a model of your own problem where you're working on, right? And what would you do normally? You integrate in time. So let's do that. So I take the model, and I have it here. So this is also in your files, which you can download. I have a, what is that, basic model, the SM91, right? This is the model, and this is the autonomous system. The SM model is the non-autonomous system, and I'm not going to do that here, but if you like to play with it, with the installation, that's fine. Now, the basic model contains all the parameters. You see this parameter, you see also the equations, right? So this is I dot, and you see all those equations here listed as they were on the slide. And now I put f mu, let's put it minus, say, 10 to the minus 3, which is in ppm per 1,000 years, right? So it's the CO2 concentration change in 1,000 years. And now let's run the model, and let's see what comes out. Oops, and you get a, of course I start from an initial state. I hope you can see those here. So this is the time series you get. So mu is CO2, it ends at about 205 or so ppmv. The ice is 70 exokilogram, and then you have here, you have the temperature, deep ocean temperature, about 4.2 degrees. So it goes to a steady state. Yeah? Boring, I think. So you throw maybe the model into the trash. But you might think, well, maybe it's not a bad idea. Maybe I'll change this f mu a little bit. I can also change other parameters. So I change the f mu. I change it a little tiny bit. I just have it. So 0.005, right? Factor 2 smaller. And then I run the model again. And let's see. Oops. 100,000 year time scale. You see this, right? Kilo years. I solved the problem of the ice ages. Correct? So this is what you do with the model, and this is of course where Salzman and Maas, of course they tuned the model, carefully so that it gave this response, of course. So this is what happens. Now you change it a little bit more. So let's change it to plus. So we just take the other sign of the CO2, and I run it again. And I get nice oscillations. And also the time scale, is still nearly 100,000 years, you see. It's a little bit longer, but very nice. And you see also oscillation between CO2, 300 and 200. It's not that bad, right? If you see look at the observations. And now I changed it a little bit more. I changed I go to a little bit more, so emissions, factor 2 bigger, and run the model again. Oops, steady state. So you see there's a tiny window in this f mu where you get perfect, perfect quote ice age cycles. Now what happens here is that you change the parameter here, f mu, here in this system, and apparently the qualitative behavior of these solutions here, they changed, right? This is the interesting idea, and that could happen also in your, in your turbulence model, where you run a model for different parameters, and suddenly you see very qualitative different behavior. You see strong oscillations at a particular frequency or not. Now this is this change is really at the heart of the sort of elementary bifurcation theory, where you think, I get transitions between steady states and periodic solutions, and I want to know, how that comes about. And then dynamical system theory gives you a nice classification. So I go back to my presentation. So we did this. So this was the summary of what we show, right? Steady state at this value, and you have even at 0 you have these oscillations, and then you have f mu. You have also, when you increase it, you have, say, again a steady state. And dynamical systems theory gives you a nice classification. When you change one parameter in the dynamical system, which is autonomous, you can only have 4 transitions. There are not more. There are 4 of them. And one of them is the saddle node. So this is the and this is the simplest dynamical system. You see it nonlinear, right? You only have this in nonlinear systems, where you basically have the simplest equation or dynamical system where you see this transition. So it's called a normal form. And you see those are baby dynamical systems, right? Dx dt is lambda minus x squared. Then the second one is the pitchfork, where you see you get a cubic term in there. And you see you have one solution here. Oh yeah, I should explain that. Yeah, I'll explain that later, what the dots and the dashes mean. You have the transcritical bifurcation, and you have the half bifurcation. And you see already the normal form here is a 2-dimensional system, which looks a little bit more complicated because it has cubic terms here too. Now let me first show you what this means, because if you've never seen this, I have to explain this, because otherwise you're sort of hopeless later on. Now let me see, the easiest one is the saddle node. So I have dx dt is lambda minus x squared. So imagine you do the same for this SM91 model. You could do the same analysis, but here it's a baby analysis because this system is much simpler. So you look at steady states. Now steady states means the x bar dt, so let's label them as x bar here. The x bar dt is 0, and you find immediately that lambda minus x bar squared is 0, so x bar is plus or minus square root of lambda. And so you see it has no solutions when, say, lambda is positive, when it's negative, and it has 2 solutions when lambda is positive. Yeah. So that's why you see in the picture that you see nothing for lambda smaller than 0. No real solutions, right? We're interested only in real solutions. So these are 2 solutions, and what you do now is you want to look at stability of those solutions. So what you do, you say, I investigate linear stability. So the amplitude of the perturbations is infinitesimally small. So what I do, I take x is x bar plus x tilde, where x tilde, norm of x tilde, is much smaller than, say, x bar. And so I can linearize in x tilde in the amplitude. Now I put that into the equations. I get x bar x tilde dt. I do it a bit extensive, but I hope it's not too offending for you. So x squared, right? Just fill in the total solution. Now the x bar dt was 0, so I'm left in the left-hand side the x tilde dt. And then on my right-hand side, I get lambda minus x bar squared. Then I get minus 2 x tilde, and then I get minus x tilde squared. But this one I neglect because it's much smaller than the other terms, and this one is 0 because of the steady states. And so I find here that this is minus 2x bar times x tilde. And so you see you have a factor here which depends on your background state, and you can already compute now that x tilde as a function of t. You can solve that. That's x0 times e to the power, now let's call this say beta, then I get e to the power beta t. And so this shows me that if x bar, I take the positive root, I see that this is negative beta, and so all perturbations damp to 0. So when I start a time integration a little bit off here, it will go back to that steady state. But if I take, say, the negative root here, so I take here, then this becomes positive, and so it exponentially diverges from that state. And so when I start a time integration somewhere here, right, it would diverge, in this case to minus infinity, and in this case it would go to the other state. So it diverges away from that state. Yeah, so this means how you draw these diagrams in terms of dashed and, say, drawn curves. Drawn curves mean that they're stable, so perturbations decay to that state. Dashed curves means unstable. And you see the different cases now that, for instance, in the pitchfork, you have, say, one stable state here, and then suddenly you get 2 other stable states which are symmetry related. You see f here minus x is minus fx, And then you get here, you get an unstable state here for lambda is bigger than 0, which is the trivial state x is 0. Now you can all do that, it's not so difficult. But you see there are only 4. Now in applications, in climate models or whatever models they do, which one would I see the most? Who has an idea about this? Because all those things have physical meaning, right? If you see, and I put that already there, this means some kind of non-existence. This means symmetry breaking. This means what they call exchange of stability. There's actually this solution, they exchange stability. And here you see there's spontaneous oscillations. Ah, that looks like something we saw in the simulation, right? In the Ice Age model. So suddenly I get spontaneous oscillations. So probably there's a Hopf bifurcation there located in that model, SM91. Now, again, my question, which one would I see the most? If you look at you know, this is in popular terms now called tipping points. And there are many papers, you know, Nature and Science, whatever, where full of tipping points. And when you look at those, they're always the same things. They're always the same guys. They're also contained here, but there's only, well, which one would I see most? Sorry? You think so? Yeah, very good. And why? Uh-huh. Uh-huh. Yeah. The answer is correct, but the argumentation could be better. You know, there's something special in the transcritical and the pitchfork bifurcation. You see that immediately looking at these pictures. Locally, you would have to have a solution here for all values of lambda. This is very rare. You have to construct that more or less. So in the GCM, for instance, they had flux-corrected models in the past. And the flux correction, when you put that on the models, you basically construct a solution for all values of coupling parameters. So there it was a construction where you constructed, and you saw in many flux-corrected models, you saw erroneous transcritical bifurcations. Now for the pitchfork, there's even more. You have to have symmetry. Now, if you look at the globe, you know, and you look at continents, you would rarely see that you have, say, reflection symmetry in model equations. Of course, when you make nice square basins, right, like Bruno does with the wind-driven circulation, you have nice symmetries and you see pitchfork bifurcations. But in general, they will be gone. So what you see is mostly Hopf bifurcations. They're really everywhere, right? Everywhere in systems you see Hopf bifurcations. And you see saddle node bifurcations. And now you don't see a single saddle node. You always see what is called a back-to-back saddle node. And it looks like this. This is the pictures in all those science and nature papers. It looks like this. You have a parameter lambda, you have a state vector x. It looks like this. You've seen these pictures many times. What's called a back-to-back saddle node bifurcation, because there are two of them. Both are saddle nodes. You have two stable states. You will see them also tomorrow and maybe in other talks also, where you have here an unstable, say, part. So why would that be? Why would you have a back-to-back and not a single saddle node? Yeah. Yeah, no, go ahead. Women first. Yeah, you get hysteresis. That's what people do. They run with a model, right, and they run very slowly in time, so they stay, and then they jump, right, and then they go back with the parameter in time very slowly, and then they jump back, and you see this typical hysteresis phenomenon. This is how you see it mostly in the papers. Yeah. Think of the physics. Yeah.
Or the model that's on the blackboard there, it's unphysical in the sense that some initial conditions lead to infinity.
Exactly. 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 You know, it's just boundedness of energy of the system. So this is you never see in physical systems. Of course, mathematical systems you can do that, but physical systems you see always back-to-back saddle nodes because you have trajectories going to minus infinity here. Okay, so I spent quite some time on it, but I hope this is clear. Yeah. Yeah. Yeah, the symmetry breaking, you know, is mostly in, You see that in models which are really, they impose the symmetry more or less. Yeah. Like if you do this is a canonical problem. Of course, in the atmosphere it's also true, but in the ocean circulation, you know, you have an ocean basin, or say L here, and you put a symmetric wind on there. So this would be the ocean circulation at mid latitudes, right? Say 10 north to 70 north in the Atlantic, and you take this as a sort of on the beta plane, right? So you take a x, y local Cartesian coordinates, and you take a quasi-geostrophic model that has perfect reflection symmetry around the mid-axis of the basin with this wind, and you'd see a multitude of pitchfork bifurcations. But it's constructed in that way. Yeah? But it's nice, because if you... exactly. That's right. But that's more complicated. Yeah. Okay. Clear to everybody? Fine. So I did that. Then the hub bifurcation is basically, you know, you have a say fixed point here, so a steady state here, and then suddenly you get here a limit cycle, so you get a periodic orbit. And so if you view that in terms of trajectories, in the, say, lambda is negative case here, what you would see if you start from an initial condition, then it would go down to the trivial state here, which is a steady state x0 and y0, which you see immediately. And once you're sort of crossing this lambda 0 boundary, what you would see is trajectories going here to this, say, ellipsoid structure here. And when you start within this initial condition, within the circle, within this, say, limit cycle, you actually converge to that too. And so you see what happens in this model SM91. You can already guess, right? That in SM92 you cross a half bifurcation with F mu changing. Because you get a limit cycle, which is this 100,000 year oscillation, you get that into that dynamical system. Now it is more complicated, which you, of course, you have to compute yourself with the lab exercise. It is a little bit more complicated than here, because there are actually two half bifurcations. And that's because if you have F mu higher, you get again a steady state. And so you have a region which is bounded by two half bifurcations. Yeah? Now, back to the physics. Here it's where it all happens, right? In the transition, in the half bifurcation, the mechanisms of amplification of the instability are clearest. This is where it's critical. So this is where you can analyze mechanisms very clearly. How, say, how frequencies, and of course when you have PDE systems, how patterns of variability are amplified in the system. It's at this point where this specifically happens. Okay, so this is again my favorite half bifurcation, which you see. This is remote controlled aircrafts, where the comes in. Very steady state. Oops. No, this is half bifurcation. Yeah, so see it again, right? You see this flutter instability, and you see. Okay, now next time you're in the plane, remember this picture. They have a safety margin in the planes, right, in terms of the angle. Good. Okay, so now the next problem is, why would you want to compute from a model like the SM91, but also some other models where you have this back-to-back settlement, for instance? Why would you want to compute actually the whole bifurcation diagram? I mean, I would say, well, you know, you just run this model and then you do a few calculations, and I see the oscillation, so I say, oh, it's a half, but why? You know, why would I do the whole thing? And computing actually try to compute this whole diagram with the unstable states and whatever. So to modify this, I show you this picture. So suppose we have a system where you have a lambda here, and you have a back-to-back settle out. So just the way I sketch it on the board, right? So if I do a sort of quasi-steady integration in time, where I take a long time to stay here and then change the forcing very slowly, so I stay near the equilibrium, then I would have a jump here to that state, and then I would go back. If I change the forcing, I would go back here, see the hysteresis. And now what people usually do, they want to study sensitivity. They want to study sensitivity to a certain phenomenon, like I change the topography in my system, or I change the forcing a little bit, or whatever you want. And then if you don't compute full bifurcation diagrams, you might lead to very wrong interpretations on sensitivity. And the picture here shows you the case. So suppose I have this as my background diagram for mu is mu0. So I have a second parameter in my system, which is, for instance, the topography or whatever. This is my reference diagram where I have a back-to-back saddle mount. And now what I do, I change mu from mu0 to mu2. And I do a simulation here, and I look at this observable here, and I see, it changes only very little. So you know the effect is not important. This is what your conclusion would be, naively. Whereas if you look at the bifurcation diagram for that case, the saddle nodes have disappeared, and so actually you get into totally different regime of behavior of that model. Right? On the other hand, if you change mu0 to mu1, and then you would do an integration for, say, from starting at b1, and you jump directly here, because there's no steady state anymore here, so you jump directly to part b2, you say, it's enormous effect. This is very important, because the whole thing collapses. But if you see that the bifurcation diagram has shifted only slightly, so the system has not changed at all. Right? And you see that only when you compute the full bifurcation diagram, you see this shift. So if you want to interested in sensitivity, right? Yeah. Earth gets angry at me now. Exactly. So this is the main motivation why you want to compute if you're interested and you have uncertain parameters in your system, and you want interested in how sensitive it is to changes in, say, parameters. You need to compute full bifurcation diagrams. And this motivates really what I'm going to do now. I show you the art of how you do numerical bifurcation analysis. This is really an art. It's not, straightforward computation in time. It's carefully looking at what happens, carefully looking at how you compute branches and how the branches split up and how they're connected. There might be isolated branches of solutions. It's really an art. And I guide you through it. It's a bit, boring in the sense that it's sketching your techniques, but if I don't show you this and you're going to work with these codes, with a lab, you don't know what you're doing. So I have to show you this. Now you can do that, you don't have to do that only with ODEs. You can do that with full PDE systems. So if you have your turbulence model and you're looking not at a very fluctuating system, right, but you're interested maybe in the means and you have a model for the mean, like mean field or whatever, you still can be interested in how steady states and how, say, oscillations of those systems appear. And so what you do, you take a system of PDEs. Now this is written very generally, so you might have a matrix M here, which might be singular. For instance, in Navier-Stokes equations, you have incompressible flows, you have a divergence U is 0. There's no time derivative there. And so when you look at the operator here, then you have a 0 on the diagonal. And so that's why normally you have the M there. Here you have a linear operator, just a nonlinear operator, which would be advection in Navier-Stokes, and you have a forcing in the system, right, which can be anything. And this can be an ocean model or atmosphere model, whatever. You discretize it in some way. Now that's your own choice, finite elements, finite differences, spectral methods, whatever. And you end up eventually with this dynamical system, which is, you can always write in the terms of dx dt here is a linear operator, nonlinear operator, and a forcing, where x is now the state vector. And in the typical ocean model where we do continuation with, the dimension of x is 1 million or so. So you don't have 3 degrees of freedom like the SM91, but you have 1 million equations, which just come from, well, you have n points in the x direction, or in the phi direction, y points in the theta direction, and a few points, say, in the z direction, and that is cubic, or quadratic in the horizontal resolution. And so you easily add 1 million degrees of freedom. Even if you do a 2 degree, say, ocean resolution global, then you have about 1 million degrees of freedom. Yeah? But that doesn't matter. I mean, you can do these techniques basically, not for, say, small systems, but also for bigger systems. The thing is, if you do bigger systems, you need a bigger computer. And you need sophisticated techniques. It's not that you can do it with the MATLAB codes which are available in the lab. So what you do, and basically you're interested in these fixed points, so that's basically the same analysis I did analytically, but now we do it numerically. So you're interested in steady states, assuming this is an autonomous system. So again, this is the right hand side. In the saddle node, this was lambda minus x squared. Now we have a general, say, system of algebraic equations. And what you do a very nice, say, you do a parameterization of an arc length. So here I sketch a bifurcation diagram starting somewhere here and ending up in a pitchfork, and you want to compute all those states here. And what you do is you take, say, you parameterize this with a curve where S lives in R, and then you have this curve in this high dimensional space, and what you do, you compute a tangent to the curve here, and then you have an initial, what is called an Euler guess, and then from there you start a iterative process to converge with Newton-Raphson. I'll show that in a minute. You converge to a solution of this algebraic system. You probably did Newton-Raphson in your class on numerical mathematics for finding a zero of a function. Now here this is, even if this is million dimensional, you can still apply Newton-Raphson to find the zero of a million dimensional algebraic system. So this is the technique, and what is nice about this technique is that you can actually go around saddle node bifurcations. You can compute, say, unstable states. Now, if you do time integration, maybe to mention that, would you be able to compute unstable states or not? No, and why not? Yeah, because if you get close to it, right, it diverges from it in time. Here, when you use a Newton process, Newton-Raphson process, that doesn't care about stability, it just cares about what is called isolated solutions. And so with the Newton-Raphson process, you can compute zeros of functions in order to which are stable or unstable. And so you can compute also the unstable branches. So you can actually follow the whole bifurcation diagram, which you cannot do with time integration. Yeah, the Newton process has a limited convergence range, and that's why you steer it basically by this Euler guess. So you can make this step length here where you actually go, you can control that, and you can stay very close to this, say, curve, or you can do a little further on depending on the Newton process convergence. So that's all done automatically. It's adaptively structured, right? If a Newton process converges quickly, then you take a bigger step, and when it converges less rapidly, you may take a smaller step. And so you try to stay along this curve. Now you see already that you have problems, right? If I would do this here, this say method here, I would go through a pitchfork here, I would just go on this branch, I would never see these ones. Right? It just follows this, you can imagine the tangent here, and so you stay on this branch, and if you don't do anything, you wouldn't even see that there's a pitchfork. Newton-Raphson doesn't care about this. So we have to do some more. Now first to show you how this is set up, so this is just a numerical formulation. So you compute this initial tangent to the curve in S, and then you solve an extended system, so you solve this, say, algebraic system on the curve, and so you see you have one more unknown, where the lambda is also a function of S, and so you need to do something in an additional normalization, which you do a sort of normalization of the tangent here. So if you divide here by ds, so by S0, you see it's sort of a normalization of the tangent, which you control actually the distance, sort of how far this tangent is extending, here along the branch. And you have the Euler guess, you take this sort of known tangent here, so let's use, this x0, lambda 0, and then you step forward and you compute the next fixed point, the next steady state on the branch. And so you follow this sort of points on the branch, and you get, say, part of the bifurcation diagram. Yes?
Could you recall the notation?
Yeah. Phi is the algebraic system. And as I parameterize now, x, the solution, and lambda as a function of this arc length. Well, you can write it as phi gamma s, because gamma s is this x and lambda together. Yeah. So yeah. Sorry, it's a little bit. This is the traditional notation. Okay. Now this is a bit technical, but what you can do is basically you can compute an initial tangent. Maybe I'll skip that. There's a technique to if you know an initial point, then there's a technique to compute an initial tangent to the branch by looking at this matrix. But I think that's not so important. Then how does the Newton-Raphson process work? If you've forgotten it, well, you start with you have a function here in one dimension, say gx. What do? You have a starting point x0. You compute the function value. Then you compute, say, the tangent curve here. So that's this g prime x times plus b. You compute the intersect here, and you compute the function value again. And you see from this picture already, this is of course the nicest function you can imagine, that this converges very quickly. And actually it converges quadratically. So every time you gain double digits when you do one iteration step. So usually it's 3-4 iterations and you converged, right? So that's very nice of the Newton-Raphson process. And now how do you do that in this extended system? Well, what you do, you compute the Jacobian here. So this is you differentiate to x, right? This is a matrix, Jacobian matrix of this phi itself. Then you differentiate to the parameter here, and you get this x dot here and lambda dot. They multiply lambda and x's. So this is the Jacobian matrix. This is this step increase, and then you get the right-hand side. So this is basically the generalization of the Newton-Raphson process for this million-dimensional system. And you see that you have to solve linear systems. So this is you can forget about this formulation, but you have to solve large linear systems of equations for this delta x and delta lambda. And you have to do that a few times in the iteration process with Newton-Raphson. Sorry? This one? Okay. Well, maybe I show that here for Newton-Raphson. So you see, if you use Newton-Raphson here, you see that this is your, if you solve xk plus 1 here in terms of xk and g, maybe I write that out. So in the Newton-Raphson, now probably you cannot see this at the back. Okay. So you have, in this case, you have xk plus 1. Yeah, thank you very much. Xk plus 1, and you see here is xk, and I get here gxk divided by g prime xk. Right, this is the one-dimensional version. And this is what you probably used in numerical math class. Now if you generalize it, you have a Jacobian, so you multiply this by, so I do the 1dk, so I multiply by gxk, then I get here xk plus 1 minus xk, and then I get here in the right hand side I get minus gxk. Yeah? And now when we look at the figure here, we see that this is our Jacobian, and this is now the Jacobian of the extended system. This is this delta xk, so that's the vector delta xk delta lambda, and then here is minus the right hand side, and you see exactly that's just minus the right hand side here, which is shown there. I hope that gives a little bit insight. Yeah? So it's just a generalization of Newton-Raphson in the n-dimensional case. Okay. Yeah, thank you, Kathleen. You're closer than I am. Now, what you have to do, I'll sketch that briefly, you want to detect bifurcation points along the way. And so, as I said, if you naively do this continuation, you will not find it. So what you do, you have to have indicators. Well, one thing you can do is there's some indicators like the determinant of Jacobian, which vanishes. Well, that's expensive for a million-dimensional system, computing a determinant. So that's not what you want to do, but in small systems you can, yes. Yeah, that's actually that's good. That's a good point. I mean, normally you would follow the branch very closely, But yeah, you could always take an orthogonal tangent, right, and actually start a Newton process. But I would guess that you would a 99.99% Newton process would not converge. So you really have to do that very carefully. And what one technique is to actually, that's, I don't sketch that, but that's how you find the other branch, is basically you detect first the bifurcation point, so you know, I'm at a pitchfork, like for instance with these indicators, or solve a linear stability problem. And then what you do, you take a tangent orthogonal, and then you try to find the branch. So there's where you do, but then you know exactly where you are. Yeah? But there's a smarter way to do it. So that I'm going to show that in a minute in practice. Now, once you have this, say an indicator of the, you solve a linear stability problem, so the eigenvalue problem, you detect that an eigenvalue goes through 0, you have a pitchfork bifurcation, and then what you do is then you start a second process to detect it. So this is exactly your point. Here's the how you switch to another branch. Well, this is what I just said, but there's a smarter way, and this is how we often use it in practice. You know that if there's a pitchfork, you have symmetry breaking. So what you do, you make the system, you first compute this curve here, and then what you do, from here, from here what you do is you make the system a little bit asymmetric. So for instance in the wind-driven problem, you add a little asymmetric component to the wind. So then you're a little asymmetric, and then what happens is that this pitchfork it breaks up. That's what we call an imperfect pitchfork. Then you do the continuation along here, and then you see that actually some norm is going up in the solution. And then from here you switch back to symmetry, so you remove the asymmetry in the system. Then you're here, and then you move back, and then you detect the pitchfork as a saddle-node bifurcation. So this is in practice how you do it for high-dimensional systems. In the codes I give you, like in the labs, it's done. It's all done this way, because you can do that easily for low-dimensional systems, but it's more expensive in high-dimensional systems. Okay, then the linear stability problem. Of course, you have to solve, as I did for the saddle node, where you have this saddle node bifurcation. You have this, say, this coefficient which changed from negative to positive. Here you have to solve a generalized eigenvalue problem, because the M is usually singular, which ends up in a B here if you discretize a linear stability into a singular matrix. And there you have to also use, say, this is the traditional, say, methodology, QZ. I mean, don't worry about it, but I just want to mention it. And then there's some more sophisticated techniques which are suited for really high-dimensional systems. And we mostly use Jacobi-Davidson QZ, which is really a targeted technique to find eigenvalues in a certain strip. And you only need 10 or so, and you can do it for, say, a million-dimensional problem. You can compute, say, the 10 which you want very efficiently. So if you have the linear stability problem, you have the eigenvalues and eigenvectors, and then from there you can compute, say, this transitical saddle node and pitchfork bifurcation by looking at a single real eigenvalue crossing the imaginary axis. And for the Hopf, you have this complex conjugated pair of eigenvalues crossing the imaginary axis, and then you compute, there's techniques also to compute periodic orbits near the Hopf bifurcation. So this sketches a bit the computations. So in the code you're going to use, this is why I show this, you have an initial point, and then you with this SM91 you're going to try to compute, say, the bifurcation diagram, and eventually you want to compute also the Hopf bifurcations, and you want to compute the periodic orbit related to this ice age problem. And you do it in this way. So this is what is in the codes. Okay. So software, the ones I put in the labs is Matcont and PyDS tool. For the Python freaks, I would say do this. Yes? Yeah. I show it in a minute. How that in the next thing, how you find that. Yeah, I didn't mention that yet. So far this is only the computation of the branches of steady states and the instabilities, so the Hopf the bifurcation points. And I show you in a minute how we actually do it for how you compute the limit cycles. Now here it is for low-dimensional systems, so if you have a problem with, like SM91 or some other Ice Age models or some box models or whatever you might like, if it's sort of dimension smaller than 2, I would recommend MatCont or, well, I'm not a particular fan of MatCont, but it's usable. PyD tool and many more are on the web available. So whatever you like, you can use that. I'm a big fan of Auto. I use that a lot for low-dimensional systems, so smaller than 100, I would say. Maybe a few hundred now, but it's a very nice, say, program. And if you do the lab, I would recommend actually using Auto, because if you want to do something which is bigger than 10, you need to use it anyway. And then it's not worth to spend all the work in terms of the MatCont or whatever, because you're hopeless if dimension is bigger than 10. So here you have the Auto, you see the whole documentation. There's all kind of, say, downloads. Oops, hey, interesting. We watched. Well, I could do that at home, but yeah, maybe I don't know why that. But there's a lot of there's versions in C, versions in Fortran. There's parallel. There's a lot of, you can do fantastic problems with it, optimization problems on very complicated manifolds. So it's a fantastic tool. I cannot be more enthusiastic about it than using Auto. And I put codes of Auto of the SM91 in the labs. So if you want to use Auto, actually the codes for the SM91 are already there. You just have to do it then. And then I set these specialized codes where we're now in about 10 million range, where we can do these things for models. And we have a sort of similar setup as Auto, but with different solvers, because you need sort of to get this dimension, you need to do a lot more work. And to show you first I still have time. Show you first the use of MatCont. I could use Auto too, but I show you MatCont because maybe many of you use that. Let's go to how that looks like. Okay. So I go to MatCont, start up MatCont. This is how it looks like. Oops. So here I already cooked up, of course, F mu versus this is I, so this is the ice volume or ice mass. You see that in the starter you see all the parameters listed and the initial point. Here's some numerics. This is the main control window. So first I show you the system. So here we see a lot of systems put in. This is SM91, right? So this is the system I put in already, and there's a lot more in there, which you might want to look at, or maybe not. So I loaded already this SM91. I have an initial point, which is constructed, which you always can do. So suppose you want to compute for here, you want to compute for the wind-driven circulation, you want to compute a bifurcation diagram, right? Now, what is always an initial solution here, an initial steady state? Sorry? Yeah, the 0, but the 0 should also be on the 0 wind. So this is what you do. You cook up what we call a homotopy parameter, so it's an artificial parameter in the system. And you start with it at value 0 where the wind is 0. And then you follow a branch of solutions into that parameter, which cranks the wind from 0 to 1, right, in amplitude. And then from there you have a good initial solution. So this is what I did also in this Ice Age problem. I put some parameters to 0, then put a homotopy parameter to get parameters back and started from that solution, and you get an initial point. So you can always do that. It's a little bit work, but you can always do that. And in many cases you can construct an initial solution just analytically, but here it's a little bit more difficult. So now, how do you do it? Well, this is compute means now it computes this branch from this initial point, and you probably will see where that's located. Now it's a very tiny curve, but you see here, and now it detects, it says hop. Oh, that's what we like. This is what we expect also. So this was negative F mu. Now, the value of F mu here, I multiplied it by 1,000, just for scaling. So 0.5 here means 5 times 10 to minus 3. Right? So this is the hop. Now I can resume here, and it computes a curve here, and that's one part of the diagram. And then I can do backward. So I start from this initial case, I run backwards. It doesn't show me anything yet on stability. It runs back. You see, there's another saddle now there. And then I have to compute again, and it says extend. And then you extend it. Should be another hop fight. Boom, there it is. And then you resume here. And you see, this is at least the diagram of the fixed points. Yeah? Now I'm not going to do more because you have to do it yourself. But this is, you know, how easy it is, basically. It's so you see already now, if you look at, we found fixed points here, so which are stable right here, and we found fixed points stable here, and we found periodic solutions between those half bifurcations. And so you can imagine there's a branch of periodic solutions which runs from here and closes here, which is exactly this ice age, say, problem, but you wouldn't have anticipated that there would be another, say, unstable state here with the two saddle nodes. You wouldn't see that from the time integrations. And this can have enormous impact when you change other parameters in the system. Yeah? Well, gives you a glimpse on how you compute bifurcation diagrams. It's really an enormous fun. I mean, I do this now for 40 years or so, and I never get bored of it, right? There's always things which are surprising, and you know, it's always different than you think. So it's an art.
Excuse me.
Yeah.
How would you, from this now, determine the stability?
Yeah, that's in the code also, where you can look at, say, I didn't switch that on, but you can do that. It's somewhere in the eigenvalue solvers or something. You know, I said already I'm not so a fan of Markant, because there's all those windows. I get always confused and then something. But it is an option. It's also an option then to choose. You can choose from here. You can choose a select a curve, and then you get to a. You can select a point on the curve at half bifurcation, and from there do a periodic solution continuation. Well, I would say do it because I want to show you more, and this is the basics. Now to show you a bit of extreme continuation, this is what we recently did. We're interested in a lot now in paleo problems, and actually what we wanted to do is, what in the past continents are different on Earth, right? So for instance, if you start 65 million years ago, the continents are really, you know, I'll show you a picture. Australia was still connected to Antarctica, and you know, the Atlantic was very small and the Pacific was very big. And you can compute a lot of those with ocean, say, general circulation models. You can try to compute, say, steady states of this ocean circulation for the different bathymetries. But you know, that's a long spin up. It's a few thousand years before you get into equilibrium. And so with continuation method, you can say, well, I try to solve for an ocean model. So this is three-dimensional ocean model, just like a GFDL model version, say, 2-degree resolution here in this paper. And what you want to do is you just change the bathymetry. So you just continue in the bathymetry. This is what I call extreme continuation. And you want to compute the steady states of this ocean model by varying the bathymetry. Now here's I'm not going to explain that in detail how you do that, but you actually make a predictor where you change the geometry already. And then, if you're interested in that, I mean, it's in this paper, which recently appeared. Now this is what is the result. So this is a full-blown three-dimensional model, but we show only here the barotropic stream function. This is the geometry of 65 million years ago, so that's the end of the Cretaceous. And what you see is that if you loop it, you change the geometry, right? And you compute, in this continuation, you compute the steady states of the ocean circulation. And you have also the full 3D meridional overturning or whatever. And you see the ACC appearing, right, because the gateway opens. I show it again. Oops. So You see the ACC is closed now. You see it opening, the Drake passage, and you see the ACC appearing. So you can do a lot of those, say, computations with it. This is also about 1,000,000 degrees of freedom, and you can. It feels like God, right? I mean, you can move the geometry around and test sensitivity very nicely, because all this geometry is very unknown. I mean, there are of course constructions, but they differ in some ways. But here also there's a very nice techniques to study sensitivity with respect to the bathymetry of certain solutions. So this is somehow state of the art in discontinuation in climate. Yeah. Well, the dynamics here is that your forcing changes here too, because we took the forcing from say atmospheric models of paleo climate simulations, and what you see here basically is the wind-driven circulation by varying, say, the wind, which changes over this period not so much, but mostly the continental geometry is changing. Right? You see here this circum-India current, which was in the end of Cretaceous. And you see India moving very quickly here, and it closes off what we call the Tethys Sea here, closes off this sea and basically cuts off this current, this called the circumglobal current, right, which went here through and went here through all the over the whole equatorial zone in the Cretaceous. So the dynamics is the wind-driven circulation here, but of course you change also the buoyancy forcing, so the meridional overturning changes too. I don't have the pictures here, but that changes. So it's just changing of the whole three-dimensional ocean pattern versus forcing. Yeah. Okay. An eddy resolving DCM is you're not interested in fixed points and individual orbits. This is the one thing. You're interested in statistics. So that's where you go to ergodic theory. This the endpoint. You're interested in PDF of things. So that's something you wouldn't want to use this sort of techniques to do that. Yeah, that is certainly useful. But if you try to find a steady state in a high resolution model, say supposing that you could do it, because then you get into the 1,000,000,000 degrees of freedom, easily. Then the steady state which you find is very different from the state which you mean state which you had in the eddy resolving model, because all the eddies they rectify the mean flow. And so this is what Ted also mentioned this yesterday on the upgrading transport of momentum, for instance. Right, you see that in the ocean too, in the atmosphere too. So the mean state is very different from the steady state. But I would guess if you're really looking at say this say flows where you actually have this say turbulent structure, and totally you're not, I mean, you're more interested in the statistics, and so you need to use other techniques. Yeah. Exactly. Yes. So you want indeed, if you see transitions, right, like in a flow state which is highly irregular, and you have a certain PDF and you change a parameter and it gets from unimodal to bimodal, you think, that's interesting. So this is then and that you want to change, you want to know those type of transitions. But that's different. I'm gonna come back to that at the end, so on Friday. But this is the elementary, say, models where you still, you learn a lot about from the mechanisms on the large scale, say, flow transitions. By solving the eigenvalue problem. So you just solve this say generalized eigenvalue problem, and you look at the eigenvalues, and when they're all in the left-hand complex plane, the solutions are stable. And for this case, they are. Yeah. What do you mean by that? Yeah. Now, here in this case, the bounding conditions are such you actually have restoring conditions from that model, and that guarantees that you solve in temperature fields which you compute in this say ocean model, they sort of strongly restore to the atmospheric forcing. And so that means that in this case, all those states are stable, and you don't have multiple equilibria. But if you have situations, of course we're working on that too, and you have really you couple it to an atmosphere, like an energy balanced atmosphere, where you have different boundary conditions for temperature and salinity, then you have multiple equilibria, and then you can just trace, different branches of steady state with the continental boundary change. Right, so that's on our list to do. And this is hopefully we can. I mean, one problem which is lingering around, and which also maybe next week is talked about, is in the meridional overturning, you see sinking in the Atlantic, and you see no sinking in the Pacific. Right? Everybody knows that. And now the question is, why is this? Why is this big asymmetry? And then most of the answer is, well, because the Pacific is fresher than the Atlantic. Right? And then you think, well, why is it fresher? And you look at the precipitation fields, and they're not so different for both. And it's evaporation which is different. And then you think, why is the evaporation so different? Well, because the temperature is higher. But the temperature is higher because the circulation is this way. And so you end up in a chicken and egg problem. We just wrote with a couple of people in a review paper, which is submitted, where we try to sort of get all the alternatives, for why you have this asymmetry. And one of the things is, well, there might be multiple equilibria. So basically, under continental, say, present continental states, you actually have the equilibrium which we are in now. Now, there might be another equilibrium, but there might also not be another equilibrium, but there might have been in the past another equilibrium, which disappeared when you changed the continental geometry. Right? So there's a preference there. And this is a nice also what you can do with these techniques to try to determine this. So yeah. Okay, any more? Yeah. Yeah, this is, I mean, the aim of this whole project is to develop a paleoclimate model, so with ice and carbon cycle. It's not yet ready, but it's working on it. And then we can actually, look at limit cycles in ice age in a more like GCM-like context. The problem always with this, it ends somewhere because the atmosphere is really, that's the big troublemaker. On the long time scale, you can use an energy balance model with moisture, and you can do that, and you can actually, but if you want to include dynamics or all that. Sorry. Yeah, exactly. You want winds, exactly. So that's a big problem to overcome. But but in terms of for instance, looking at past transitions where you go. I mean, there were periods on Earth until 35 million years ago. There was no ice on Earth, and so, for instance, studying why there's ice inception on Antarctica, which happened when Australia sort of when this opened here, you got ice on Antarctica. And those problems you can study very well with these models. But ice ages will be a little bit more tough, I think. Yeah, but it's it's also tough with other models. Even now, people do these Holocene simulations, which take ages to really run. No one's done a full-blown glacial cycle simulation with a CMAP3 model or so, CMAP4 model. So that's still also very difficult to do. And if you go to higher resolution, and you're talking about eddy resolving resolutions, you will when you will retire, that will not be happened, I think. I mean, that's an extreme simulation where you run 100,000 years with an eddy resolving model. So these are sort of complementary techniques. Any other questions? I'm a bit out of schedule now, but it's. I want to show you because it also asked how compute, say, periodic solutions, and this is done in the same way with these techniques. So you know that near a Hopf bifurcation there must be a periodic solution. Now what you do, you don't know the period, although you have a good estimate of it from the eigenvalues of the Hopf bifurcation, but you don't know it. So what you do, you rescale time to get the period as an unknown parameter in the problem. And then you have a boundary value problem because it is periodic. So at period 1 here in the scaled system, the solution has to be the same. Then you use this, say arc length normalization. You now use, you integrate along the orbit to have a tangent normalization. And you have a phase condition, which is basically needed because you have an invariant along the orbit, and you have to fix the phase of the orbit. And now you have to solve this problem, and you see, well, it gets a little more extended. You have to you get a boundary value problem, but when you discretize this in time, you get about, say, so you take, for instance, 10 points in time or so. Then you have to solve 10 times the original dimension. You have to solve algebraic systems. So if you have an SM91, you have, say 3 dimensions, and you take 10 time points, you get 30 dimensional problems, and you can decouple them, and you can solve them in a systematic way, as is done in MATCON, for instance, and then you can solve these periodic orbits. And continue just the periodic orbit without doing any time integration, right? This is the nice thing about these techniques. Now there's another way to do it. When you have a periodic orbit and you take a section here, which is not tangent to the orbit, you can compute actually a return map here, where the orbit intersects this section here, Poincare section. And so you can define a mapping here, a discrete mapping, which is called the Poincare mapping, and you can compute fixed points of this Poincare mapping. And so this is how you transfer back the computation of periodic orbits to computation of fixed points, but then of maps. Now the problem here is how to construct this Poincare map, and also there the techniques in auto, they construct the Poincare map explicitly and compute actually the fixed points of the Poincare map, so they don't solve the boundary value problem. And that's also, I'm not going to explain that because it would be very technical, but it's possible to do that. And then, of course, to finish up, you want to also introduce stability of periodic orbits. Now this is how the mapping looks like. So this, for instance, the F is here the Poincare vector field, so the Poincare map. And then what you do, you look at fixed points again. You look at linear stability of those fixed points, so you perturb them. And then you get a mapping here where the J is the Jacobian of the Poincare map. And then what you do, you see that already, that if you have a discrete map here, you can bring it up to, you can diagonalize it with this, say, T transformation. And then you get eigenvalues here on the real part here, and you see already that if the norm of this eigenvalues is within the unit circle, you have a stable, say, periodic orbit. And then there are 3 possibilities of destabilizing it. So one is you get there's an eigenvalue here which crosses the unit here, so along a real part here, and it gives you just, for instance, a transcritical bifurcation or a pitchfork or a saddle node of a periodic orbit. Right? So you see a periodic orbit making a curve, like a saddle node. And your other one is here you get along -1, and you see already if it's -1, you see it from the equations already. If this is -1, you get Z2 is minus Z1, but C3 is again plus Z1. And so you see a flipping, and that's the period doubling. So this is how you get period doubling into the periodic orbits. And then there's another where you have a complex conjugate pair. It goes along the unit circle here, and then you get a quasi-periodic behavior. So you get the torus as a geometrical object where the orbits are located. So these are pictures. There are even pictures from Eric, I think, who's here in the audience a long time ago. So for instance, if you have a cyclic fault, so that's a saddle node of periodic orbits, right? You have a stable periodic orbit and unstable periodic orbit. You can have a cyclic pitchfork. You have a period doubling where you have a doubling of the period, and then this is the what is called the Naimark-Zucker bifurcation. You get a torus, and so you have a motion which is the periodic orbit originally, and then you get a motion which is spiraling along the torus. So you see when the system gets more time variability, the geometrical objects get also more complicated. Yeah, but still a torus, you can still imagine, how that looks like. And then in my last minutes, you can imagine that if you say look at further transitions where the torus gets unstable, for instance, that you get many more complicated, say, transitions. Now there are several routes going through what we call chaotic behavior. So there where you get sensitive dependence on initial conditions. And you can have another bifurcation from the torus. So that's called the original 3-frequency route, where you get, say, very complicated behavior. That's actually the Ruel and Takis scenario of turbulence, which is sort of suggested in the 70s, early 70s. And then you have period doubling routes, the quasi-periodicity route we'll see later, so I'm not going to do that more. You have global bifurcations where actually pitchforks and hops collide, and you get a global bifurcation effect. You have intermittency and you have crisis and whatever. So there are many ways where the system gets very complicated. And I'll stop here because otherwise we don't get time on the break, and I'll still have time tonight to go on. Thank you for now.